Right, and the next talk, and actually final talk of Papel, is a distinguished paper on polynomial approximations by Jay Lim and Santosh Nagarakat. And I believe Jay is going to tell us all about it.
Hello, thank you for the introduction. So, my name is Jay, and today, with my advisor Santosh Nagarkate, I would like to tell you how to correctly approximate elementary functions for multiple representations at the same time. All endeavors in science use math libraries to approximate elementary functions. For example, this e to the power of x function is used in many domains, such as machine learning for sigmoid functions and digital processing for fast Fourier transformation. Unfortunately, mainstream math libraries do not produce correct results. And you might be thinking, well, they're still pretty accurate, so what's the big deal? But the big deal here is the reproducibility. For example, let's say you have an application that uses math libraries and elementary functions. You want to build it on two completely different machines running two different math libraries. And if these two math libraries do not produce correct results, then what could happen is when you run this application, the same application on two different systems, the output will be different. In contrast, if you were to use correctly rounded math libraries, you could resolve this issue. So in the past few years, our goal has been to create correctly rounded elementary functions. Now there are several work in creating correctly rounded math libraries, but in the context of the RLibM project, we've been making a case for generating polynomials that approximate the correctly rounded result of f of x. And we frame the problem of generating this polynomial as an LP problem. So far, we have been successful in generating several correctly rounded elementary functions for the 32-bit float representation using the round to nearest pi goes to even rounding mode. But now everybody is designing their own representations. For example, bfloat16 from Google and TensorFlow 32 from NVIDIA. And on top of that, people are starting to use different rounding modes like round to zero for more efficient hardware implementation. And our goal now in this presentation is to create correctly rounded elementary functions for all of these representations and rounding mode. Now, if Santosh had 20 PhD students, then we could probably ask each of them to create an implementation for each representation, each rounding mode, and each elementary function, but he really only had me working on this project. And even I graduated with PhD last summer, so this strategy isn't really going to work out. Instead, what we're going to do is we're going to propose a technique that generates a single polynomial that produces correct results for all of these representations and rounding modes. And the key insight is that if you want to produce correct results for all representations up to n bits, then you would generate a polynomial for the n plus 2 bit representation using a rounding mode called round to odd rounding mode. And to we're also going to propose a technique to efficiently identify special case inputs so that we can generate a more efficient polynomial. The resulting math library we created, which you call rlibmall, not only produces correctly rounded results for all of these representations and rounding modes, but is faster than mainstream math libraries. So now before I describe our cool new technique, let me go through some background and describe what correctly rounded result is and how our previous rlibm technique has been generating polynomials. Consider this real number line and some adjacent 32-bit float values. Typically, elementary functions cannot be exactly represented in floating point representation, and it has to be rounded using a rounding mode. In this example, we're using the round to nearest pi goes to even rounding mode. So V2 will be called the correctly rounded result of log2 of x1 in the float representation using the round to nearest pi goes to even rounding mode. An elementary function that produces correctly rounded results for all inputs would be called a correctly rounded elementary function, and a math library consisting of correctly rounded elementary functions is called a correctly rounded math library. Now, there are two main ways in generating correctly rounded elementary functions. The first, the first, the first method is a minimax approach, which the first method is minimax approach, which generates a polynomial that minimizes the maximum error compared to the real value of the elementary function. Unfortunately, this method does not provide the largest amount of freedom in generating a polynomial that produces a correctly rounded result, which may result in a larger degree polynomial with lower performance. In contrast, in the RLibM project, we've been making a case for approximating the correctly rounded result and generating a polynomial. The intuition is that there's a range of values in the vicinity of there's a range of values in the vicinity of the correctly rounded result where all values in this interval round to the correctly rounded result. This interval is called the rounding interval. And it suffices for the polynomial to generate any value within this interval to produce the correctly rounded result. So how has our Arleben project been generating polynomials? Given an elementary function f of x, a representation, and a rounding mode, the first step is to compute the correctly rounded result of f of x using an oracle like the MPFR math library. Then each of the correctly rounded result, you would identify the rounding interval of each of the correctly rounded result. This rounding interval defines a linear constraint on the polynomial that we wish to generate. So we encode these linear constraints into a system of linear inequalities and use an LP solver to generate a polynomial. This polynomial is guaranteed to produce the correctly rounded result for the chosen representation and rounding mode. Now, our question is, how do we extend this Arleben approach to produce correct results for multiple representations and rounding modes? At first glance, one way that we may be able to do is to use a correctly rounded math library designed for a larger representation. For example, let's say we have a correctly rounded math library for the 64-bit double type, and our goal is to produce correct float result. Then we can take the input in float, convert it into double, use the math library for the double representation to produce the output, which will be the correctly rounded result in the double representation, and then round this result back down to float. But the problem is this does not guarantee to produce correct results because of what is known as a double rounding error. More specifically, when you perform double rounding or round the original real value down to the double representation, and then subsequently round this result down to float, you're not guaranteed to produce the correct result that you would get if you would take the original real value and round it straight down into the float representation. And the reason is because when you perform double rounding, you lose certain information about the original real value. And then this loss of information causes double rounding to produce wrong results. So our goal then is to retain this information even when you perform double rounding. So how can we do this? Let's say our goal is to produce a single polynomial that produces correct results for all representations from 10 to 32-bit. Then what you do is you generate a polynomial for the 34-bit floating point representation, which only has 2 additional precision bits compared to the 32-bit float representation, using a rounding mode called a round to odd rounding mode. Now, in this example, I'm using 32-bit and 34-bit floating point representation, but this technique is general. So if you wanted to produce correct results for all representations up to n bits, then you would generate a polynomial for the n plus 2-bit floating point representation using the round to odd rounding mode. Now, this round to odd rounding mode is a non-standard rounding mode that really hasn't received the attention that it really deserved, and has only been used in a couple niche cases like correctly rounding decimal fractions to binary fractions, and then computing primitive operations in extremely large extended precision and rounding it to smaller representation to still produce correct results. And the question here is, why has it not been used for elementary functions? Well, the previous techniques have been using the minimax approach that I described before that generates a polynomial that minimizes the maximum error compared to the real value of the elementary function. So if you want to generate correct polynomial, then you have to employ some form of error analysis. And to integrate the round to odd mode with the minimax approach, you now have to develop some novel error analysis technique. In contrast, if you're using the Arleben approach, what we do is we approximate the correctly rounded result itself. So it doesn't matter whether we use round to nearest tie goes to even or round to odd rounding mode. So integrating the round to odd mode with the Arleben approach is much more straightforward. Now, before I talk about how to integrate this rounding mode with the Arleben approach, let me first describe what round to odd rounding mode does. In this rounding mode, when you're rounding a real value, if the real value is exactly representable to the floating point representation, then you represent it with that value. Otherwise, you round it to an adjacent floating point value where the bit pattern is odd when you represent it as an integer. And the really cool thing about the round to odd mode is when you perform double rounding by first taking the real number, rounding it down to the 34-bit floating point representation using the round to odd mode, and then subsequently round this result down to float you're guaranteed to produce the correctly rounded result that you would get when you round the original real value straight down to float. Now, with the understanding of the round to odd mode, now let's talk about how to integrate this rounding mode with the RLibM approach. The new RLibM approach is still pretty similar to the old approach with a few key differences. For each of the input, we're still going to compute the correctly rounded result of the elementary function, but now in the 34-bit floating point representation using the round to odd rounding mode. And for each of the correctly rounded result, we're still going to compute the rounding interval, but now with the now in the context of the round to odd mode. Now, one of the things that you might one of the challenges that you might encounter when computing the rounding interval is that you might get some singleton interval. This means that the rounding interval only contains a single value, and your polynomial has to produce this one single value. This happens when the real value of the elementary function is exactly representable in the 34-bit floating point representation, and the bit pattern of that value is even when you interpret it as an integer. And producing this one specific value, and generating a polynomial that produces this one specific value, even for a few inputs, is a really challenging problem, especially considering that you also have to satisfy millions of other rounding intervals for all the other inputs. But consider that you get singleton interval when the real value of the elementary function is exactly representable in a floating point representation. And all floating point representation, all floating point values are rational values. So what we're really looking at is we're getting singleton interval when the real value of the elementary function is a rational value given a rational input. So then, how do you find out when an elementary function produces rational values? Well, there's tons and tons of mathematical results and number theories about when elementary functions produce rational values. For example, in the case of log2 of x, you would get rational values if the input is a power of 2. So when you receive an input, you would check whether this input is a power of 2. If it is, then this must mean that it will produce singleton interval, so then we can filter them out as a special case. Now that we're left with a list of non-singleton intervals, we can go back to the RLibM approach and encode these rounding intervals into a system of linear inequalities and use an LP solver to generate the polynomial. Using this approach, we created RLibMall, which consists of several elementary functions that produce correctly rounded results for the 34-bit floating point representation with the round to odd rounding mode. In our experiments, we're interested in two questions. Do these elementary functions really produce correct results for multiple representations? And if so, how fast or how slow are these elementary functions? To measure performance, we compared RLibMall against Intel and glibc math library, which are the two most widely used math libraries, and also against crlibm, which is a correctly rounded math library for the double representation. Our experiments showed that RLibMall does indeed produce correctly rounded results for all representations containing up to 8 bits of exponent bits and up to 23 bits of mantissa bits. So this would be all representations up to 32-bit float representation. This includes more than 160 different floating point representations, but not only that, RLibMall produces correctly rounded results for all 5 IEEE 754 standard rounding modes. If we were to use the good old Santoshi's 20 PhD student method, then this would have been equivalent to creating 800 different implementations for the different combinations of floating point representations and rounding modes. In contrast, state-of-the-art math libraries like glibc, Intel, and crlibm do not produce correctly rounded results, at least for some representations, some rounding modes, and some elementary functions for some inputs that we have tested. And the reason, again, is because of the double rounding error that RLibMall has avoided by using the round to odd rounding mode. Our experiment has also shown us that RLibMall functions are fast. In this graph, for each elementary function, we're going to show the speedup of RLibMall compared to the glibc math library. Speedup above 1.0 means that RLibMall is faster than glibc math library. On average, RLibMall has 1.05x speedup over glibc's float math library and 1.1x speedup over glibc's double math library. Now, based on our experiment, glibc math library produces wrong results for hundreds of millions of inputs, but RLibMall produces correct results for all the representations and rounding mode that we have tested. But still, RLibMall is faster than glibc. Now let's compare RLibMall against the Intel math library. On average, Intel has 1.3x speedup over RLibMall and 1.5x speedup over uh, RLibMall has. Let me step back a little bit. Sorry. RLibMall on average has 1.3x speedup over Intel's float math library and 1.5x speedup over Intel's double math library. Now you might be wondering why RLibMall has higher speedup compared to Intel than glibc. And the reason is because the Intel math library produces more correct results than glibc math library. And Intel is paying the price of this higher accuracy with performance. And this is the reason why RLibMall has higher speedup over Intel compared to glibc. Now that we compared RLibMall against the two mainstream math libraries, let's compare RLibMall against the correctly rounded math library, crlibm. On average, RLibMall has 1.9x speedup over crlibm. Now remember that crlibm is a correctly rounded math library for the 64-bit double representation. Since crlibm has to produce such an accurate result, it's paying the price with performance. And this is the reason why RLibMall has highest speedup over crlibm compared to the other two math libraries we have tested. But the whole takeaway in our experiment is that not only does RLibMall produce correctly rounded results for hundreds of representations and rounding modes, um, uh, hundreds of representations and rounding modes, but RLibMall is faster than mainstream math libraries. In conclusion, what are the key takeaways for this entire presentation? Let's say our goal is to generate a single generic polynomial for all representations of up to n bits. What do? We generate a polynomial for the n plus 2-bit representation using the round to odd rounding mode. And to efficiently identify which input will result in singleton intervals, you would identify when the real value of the elementary function is a rational value. Our resulting math library, RLibMall, not only produces correctly rounded results for hundreds of representations and rounding modes, but it's faster than mainstream math libraries. Now that we actually have correctly rounded math libraries for hundreds of representations, perhaps it's now a good time to revisit the standard and make correctly rounded result mandatory rather than a recommendation. Thank you very much. RLibMall is available online and we're continuing to improve it. So if you're curious, please give it a try.
Thank you. We will now take questions either online or in the room. Okay, here's one. All right.
So the question is, could you explain why it is guaranteed to produce correctly rounded results, even though results may be rounded in intermediate steps of computing the polynomial? Would it be possible to elaborate a little bit more on this question?
Okay, let's wait to see if Jules asks a follow-up question. In the meanwhile, I have another question. So I remember from undergrad classes that sometimes you have pre-computation tables and stuff like that on some architectures, in particular Itanium. And is it correct that you're completely bypassing those methods in favor of just one polynomial to rule them all?
So nowadays, the state-of-the-art math libraries and also RLibMall math library uses kind of a combination of pre-computed lookup tables and polynomials. So specifically, there's this whole world of techniques called range reduction techniques. And the whole idea is you would take inputs from the entire domain and try to map it into a small domain because polynomials are much better at approximating inputs for a smaller domain. And in these cases, one of the most common methods of performing range reduction is to use some lookup tables and so on. So our math libraries do have some lookup tables, but they're in the order of a couple hundred 300 entries for the table.
Okay, let's put up the question from Jiangsha on the screen.
Oh, right. So the question is, how difficult is it to treat singleton interval for functions other than log2 of x? That's a very, very good question. Um, so one of the example that Zong is using is sine of x. We actually haven't created correctly rounded elementary functions for sine of x. I couldn't say for that one, but in most other cases, it's surprisingly not too difficult. So for example, if you take e to the power of x, for an example, it's actually mathematically proven that the result of e to the power of x is going to be irrational for every single input except for x equals 0. Another example, and so one of the harder example is log 10 of x, in which case you would get singleton intervals if the input is a power of 10. And actually checking whether an input is power of 10 is a lot more difficult, mechanically a lot more difficult than you would think, for compared to checking whether an input is a power of 2, because in that case you only have to check whether the mantissa bits are all 0. So in some of these cases we do actually have to resort down to having a lookup table of the list of inputs that will produce singleton intervals.
All right. I think we are done with questions. Anyone else in the room? All right. Well, this was the last talk of PAPL. Let's thank the speaker again.